Hey there YouTube, Far North Racing here. So the next stage of the CNC conversion project for this lathe is we have to figure out how to move the carriage back and forth. On the stock lathe, there's this long Acme lead screw that runs down the center of the ways, and the operator turns this handle over here to move the carriage back and forth. And that would be a simple enough thing to motorize by just replacing the hand screw with a motor, except we have two problems. The first is that this handle has actually been bent. It's been hit with something heavy and it's now off axis. And that's going to make driving with a motor problematic because there's no really good way to straighten it back out again. The second problem is that the lead screw itself has a lot of backlash in it. There's a lot of slop. And there's no really good mechanism in the OEM design to be able to take that backlash out. So what we're going to do is we're going to replace this lead screw with a CNC style ball screw that both gets rid of backlash and also reduces the running friction, which helps out the motor when you're under computer control. So let's have a look at this project and see how we did it. So the first part of a ball screw conversion is you need to source yourself a ball screw. And because ball screws are complex enough devices that you can't build one yourself, that means you need to identify a supplier or a subcontractor who can produce one for you. As soon as you're talking to subcontractors, they all work off of drawings, so you have to produce a drawing that represents the part you want. In the case of a ball screw, this is pretty easy because ball screws are more or less standardized. All you have to do is figure out the length of it and then give them the overall length and they're good to go. In my special case though, because we have that grease fitting bearing on the end that we have to pass through, there's an extra little step of machining on the end, this spot right here. So I drew up a quick drawing in SolidWorks, passed that off to a couple suppliers and got some quotes, and after that I was able to pick the supplier who was best able to meet the price point that I wanted. So let's have a look at that process. So this is a supplier I ultimately chose, a guy who goes by the name of Linear Motion 2008 on eBay. He imports in Chinese ball screws. You can see here that I sent him my drawing. He gave me a quote, and he basically puts up a single item on eBay for you, and you pay him the money, and off it comes. Includes the bearings it needs to support on both ends. And sure enough, it showed up. So one of the design elements of the OEM lathe lead screw design that I didn't like was that the left-hand edge of it is just floating free in space. It's not supported. I want to have the ball screw supported on both ends, and that means I need some way to locate a bearing that holds the end of the ball screw. That bearing is a standardized design. It fits a standardized pattern, but I need something that straddles the two rails and holds the bearing in place. So that's what we're looking at here. This is the design of the bearing block that will slide over those two rails and hold the bearing block in the center. You can see how the two holes are through on the end to hold the rails, and the center one is just a little bit of a cup to hold the bearing block. We've designed this in Fusion 360, and while we can't cut it on the X-carve because the X-carve isn't big enough, what we can do is do the layout, and we'll show that on the machine in a second. Okay, so here we have the metal block that is going to be the bearing support block for the ball screw. And what we've done is we've done the layout on this block using the X-carve. So we designed the part in Fusion 360, and then using the X-carve with a V-bit, we've just come down and we've spotted the center of all the holes, and we've also traced the outside of the three major bores here as well. You can just barely see this one here. These ones here are a little more defined. This here is the cut line for the saw once we're all done. The idea here being is that the X-carve is very precise in its layout, so rather than having to do all the work of doing layout with Dicom and then measuring with rulers and micrometers and scribers and hermaphrodite calipers and the rest, here we just plug it into the X-carve comes down, goes zap, 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 carve, 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 and now we've got our layout perfect. And we can go ahead and you see we've done there. So that drill is spotted in the center of that right there. This bore is for one of the bars the carriage rolls on. This bore is for the support bearing that supports the ball screw, and this bore is for the other bar of the bar bed lathe. You can either slide it on, or I may part it and use a clamp mechanism. I haven't quite made up my mind yet. Bottom line is we need this relationship between this bore and this bore and this bore to be as close as we possibly can, because otherwise when we clamp it down on the bars, we're going to move it, and that's going to throw the lathe off. So we want this to be as accurate as we can get away with. And well, I have this piece of shit, so we're going to do the best we can with it. So what I've done so far is it's been mounted in the vise. It's been squared up using the face mill, so it's nice and flat. and mostly square to each other. And now I've gone ahead and taken an indicator and indicated along this surface so that this corner to this corner is accurate to within 0.5 of an inch, which means that the carriage from this side to this side to this side, as I move the carriage back in this way, it's going to track the center line of this bar. Or, in this case, what the center line this tracks is the new center line of the bar. If it doesn't really matter if this surface and this surface are parallel, it doesn't really matter if the distance between here to here and here to here is all the same. What matters is the center line of this bore to the center line of this bore needs to be 50 millimeters. The center line of this bore to the center line of this bore needs to be 100 millimeters. And the bores this way and this way need to be parallel to each other. And if we don't move the machine, we're good to go as far as that's concerned. Because whatever angle this does, assuming that it's perfect, it should be okay. It's probably not because this machine sucks. But the angles should be consistent to each other. So even if they're off a little bit, the angle should be okay. And then afterwards I can measure it and maybe dress it up if I have to. To prove that, up here I've got my DRO. I should be able to crank this down 50 millimeters. 45, 47, 4995, 98, 99, 50. And I drop that, and it drops in the bore, just like that. And the next one I should be able to go 100. 95, 6, 7, 8, 9, 57, 63, 75, 100, and she's in the bore. So we're good. Our setup is as good as we can possibly get it, and now we get to go ahead and cut. For the actual cut itself, we have this 30mm annular cutter, which does a really good job of cutting large diameter holes with less machine power. And because its bore is finished all the way through, it should give me a nice accurate bore both for this one and for this one over here. This one here we're going to drill out a little ways and hit it with the boring bar a little bit later on. All that's left to do now is cut it, so let's give it a shot. So there we are, there's our nicely finished bore. Goes all the way through perfectly. And we also get this really cool aluminum slug that it makes in the center. It's great, you don't waste that aluminum. I can make something out of that later on. Let's cut the next one. So we finished the two locating bores that will clamp down over the bars on the bar bed lathe. Just gone ahead and used the annular cutter on it all the way through, and we're right to size just like we need it to be. The last one we have to do is this center bore for the support bearing and the 4 holes that we use around the outside to bolt it down. This is not going to be a through hole. This is just only going down enough to get around the bearing housing. So instead of using an annular cutter on this one, we have to drill out the center and then take it out to size using the boring head. So let's do that next. Here's an example of why I hate this machine. I've gone ahead and swapped out the annular cutter holder for the drill chuck. Put in a pin drill so I can use it as a marker, and moved it over so that it's exactly 50 millimeters between the center line of this hole and the center line of this hole as recorded on the DRM. And when I drop the quill in, you see, bang, we're dead on. So, yay! Except that, in order to get the boring head in here, we have to carve out some of this to get room for the boring head to work, because a boring head can't work on a hole unless there's already a bore established. So you drill that out with another drill, get it wide enough so you get the boring head in, and off you go. And this is a 1/2 inch screw machine length drill. And you can see that even all the way up inside the chuck, that's too long to fit in there. And that means we have to move the column. We got to pop that off, we got to raise it. You can see the screw on here where it raises, and up it goes. Normally, not that big a deal if you have a square column mill, where the head always rises in parallel because the column is square. This is not a square column mill, this is a round column mill, which means the second I break that off and start moving this head can swing back and forth here. And one of the keys to getting decent work out of a crappy machine is to never break the setup. So that way, if it's, you know, you got backlash in it or randomness or whatever weirdness is going on, once you've clamped the thing down, you've limited its ability to move in certain directions. So I can go back and forth on this axis here because it's locked down, and I know that it's not going to stray from the center line. That center line may not necessarily be parallel to this surface, but it's repeatable back and forth. So that way, all the error on this hole, all the error on this hole, all the error on this hole are all the same. It would offset it up or down a little bit, but what I care about in the design is the relationship of the center line of this bearing to the center line of these two bars. So as long as I got this locked down, I can't go wrong. The second I break that setup, I've now moved this a little bit in one direction or the other, and although I can try really hard to get it back, there's no indicator on this. There's nothing on here I can use as a reference to show where it is. All I can do is drop the drill down into the pin mark that I've made, get it so that it seems even, and hope for the best. The accuracy on that would be a few thousandths either direction. It is what it is. There is some slop in the bearing that helps me out there. It doesn't have to be dead on perfect. But if I had a proper machine that had a square column, all I'd have to do is move the column or move the knee, and it wouldn't be a problem. So something to keep in mind if you're looking at buying yourself a hobby machine is to look at these sorts of things and figure out the so whats that come with the design of the machine. Anyway, let's get the head moving and get this thing reset. Okay, there we go. The head is now all the way up, and I've batted it back and forth until I got this thing lined up. And now you can see I drop that pin drill and it drops right into that spot mark. So that's about as close as I can get it. Let's see if we can go ahead and get a hole cut. So here we are with the boring bar in place. I've already been doing some test cuts just to make sure this boring bar works, because this is a brace carbide tip, which isn't the best for aluminum, but it seems to be doing a good enough job. So there we are. So we're just going to use this to take out the diameter. It's slow going because you can't take out huge cuts, and because I'm trying to make sure that I don't take off too much. Yeah, so let's go ahead and do a bore. And that's all there is to it. Nice surface finish. That little stutter you hear is when it flushes out on the bottom. Cuts a nice square shoulder there. So we just keep doing that until we've snuck up on the diameter we want. It's supposed to be 34 millimeters. I'm going to bring it out to about 33 and then stop until such time as the bearing gets here, just so I make sure that I don't go, just in case the spec they've given me isn't necessarily the actual spec for the bearing. So we've taken this bore out to 33 millimeters, which is knocking on the door of the outside spec of the bearing, and I'm not going to cut it anymore until I have the bearing in hand, so I can match the outside bore a little better. But you can see that this is working. We get a nice surface finish on here. We've got a nice flat space on here, and it is concentric to our layout line that we did with the X-carve. So this is looking pretty good. So all I have to do now is wait for the bearing to get in, so that I can double check the outside diameter and double check the bolt circle, and then we can finish this bore, drill and tap these holes, slice this edge off, and mount it to the lathe. So we're almost done. Okay, so here we are. Here's the finished ball screw bearing mount in place on the lathe. You can see here, this is where that bearing fits in. That's the end of the ball screw, known as the floating end. And all we did was just put the ball screw in, put the snap ring on the back that holds it in place on the bearing, slide this up so it clicks in the bearing, tighten down the 4 screws, and Bob's your uncle. In order to get this on, because I couldn't take these bars out, I had to use the bandsaw and slot in underneath, which gave me these pieces here. That raises the possibility that you could then mount that underneath with a clamp to lock it in place. But it turns out that because there's a little bit over center on these things, when it gets pressed down, it actually pops into place like a snap. So as of right now, it doesn't appear to need the clamp. I may do that in the future just to add some extra security, but as it sits right now, she's locked in place and good to go and holding the bearing down. It helps too that there's nothing that's a force trying to pop that off. The tension in the ball screw is trying to pull it down, so that helps to hold it in place too. So all that work comes to fruition. I love it when a plan comes together. Okay, so here we have the attachment of the ball nut right here to the carriage right here. This steel strap here is the OEM attachment for the carriage to its lead screw. This hole back in here had a brass nut fit into it that the lead screw thread through. These two slots allow the strap to move back and forth a little bit to allow you to move the nut laterally, and these two screws here clamped it so that when this was in place, you squeezed down on it with that, it locked it in place vertically, you moved it back and forth horizontally, tighten these two screws up, and that's how it attached. So to attach the ball nut to the carriage, I used the same mechanism. The only difference is that I took advantage of these two clamping screws, and I made this plate on the X-carve that picks up these two bolts on the flange from the ball nut. It goes through this plate, and then the plate is slotted so I can move it up and down a little bit relative to this. So now I have the two slots in here to go laterally, I have the slots in here to go vertically, and you just kind of assemble the whole thing, put it in loose, let it find its center, tighten it up, Bob's your uncle. The only bit of trouble I had with this was that the upper surface of the ball nut flange, which is mirrored on the other side, was interfering with the underside of the carriage a little bit. I had to knock a 1/16 of an inch off, and it turns out this is hardened. So my high-speed steel mill wouldn't touch it. It didn't even scratch. Instead I had to use the old-fashioned grinding wheel, which made short work of it. So yeah, there we go. Ball nut, adapter plate, OEM carriage mount. And it's hooked up. This whole thing was actually really very easy, and doing this part on the X-carve meant that everything just lined up and worked perfectly. I'm very pleasantly surprised with how quickly that went together. The first design worked, and my secondary design, which was going to try and replicate the nut with a little boxy aluminum thing in there, turns out to be not necessary because this plate doesn't flex at all. It's too short up in here to get much flex. So that worked. Okay, let's look at the third part. So here we have the business end of the ball screw. On the OEM lathe, this ball screw was in fact just a regular Acme screw, and there was a crank handle on this end that you turned, and that's how you move the carriage back and forth. So we were able to take that design and steel it in order to attach the stepper motor right here. So I had this particular ball screw custom machined to fit the OEM pivot. This here is just a bushing inside here with a grease fitting that just fits on there. This is the standard way you mount that, is with a bearing. So I've actually kind of done a belt and suspender sort of approach where I have a bushing here with grease, and then I have the bearing block that captures on the end. This is just screwed in like that and locks it in place. This nut holds the bearing down, and it also tightens up between here and here. So this whole thing, there's absolutely zero backlash in this system whatsoever. Moving on from there, you have a flex coupler in between it and this NEMA 34 hybrid stepper motor. And then we have the mounting bracket, which is an aluminum plate cut on the X-carve to mount the OEM NEMA 34 mount pattern. And then just a piece of angle aluminum that bolts onto this piece of steel that locates the whole thing in place. And this mount is sized to rest on the table so that the whole thing is nice and solid. With this eventually being bolted down, this whole mount's not going anywhere. It's nice and rigid. And we have the flex coupling in here to take up any misalignment there might be. Although right now, she's on there pretty good. So with that in place, we can drive a ball screw. And when we drive the ball screw, we can move the carriage. In fact, let's do that. All right. So we have ourselves a live stepper motor. That stepper motor is connected to a ball screw. That ball screw is connected to a carriage through the ball nut. And the ball screw is also supported on its other end by a bearing block. And we also, as we saw in the last video, have a motor that's working under computer control. And thanks to the fact that we have a compound slide where we can advance the tooling manually, at least until I get the belt that fits this, that motor mount is all working, it's ready to go. The tooth belt that it fits into is a little too long, so we'll have to wait for another time. We'll see a video on that when it's ready. But I think we can cut chips. Yeah, that works. I wonder what happens if you try running the program. Well, I'll be damned. Looks like we got ourselves a lathe. You know something? I didn't think that was going to work. It's nice when something surprises you like that, isn't it? Like and subscribe if you agree. Anyway, I think I'm going to go in the house and have me a celebratory beer. Because I'll be damned if that didn't work. There we are. Thanks for watching.
Let me grab my beater.